All right. Good morning, everyone. If everyone wants to have a seat, and we'll go ahead and get started. So, morning and welcome everyone to the 2017 Illini Motorsports Unveiling Ceremony. My name is Rex. I'm the team president here. Alongside me is the team captain, Tony Klepacki. And we'll be going over several things today. We'll go over the team a little bit first for those of you who are parents out there to see what your kids have been doing all year. But also we'll be going over our design goals and team changes throughout the year, as well as subsystem overviews. And then finally we'll unveil the car and allow everyone to come up for photos and questions. So what is Formula SAE? It's a collegiate level competition where students design, build, and compete a Formula-style autocross race car. We compete against over 120 teams from around the world. We compete in two competitions, the first of which is in May in Michigan International Speedway, and the second of which is in Lincoln, Nebraska. So our team is comprised of about 60 to 70 members, over 85 active, usually at the beginning of the year that slowly go down. But we're comprised of mostly mechanical engineers, but we also have a variety of engineers as well. Aerospace engineers, electrical engineers, computer engineers, as well as some non-engineers. So we like to think of ourselves as a very diverse group because a project like this is very interdisciplinary. In addition to just being a student organization, students can also elect to take class credit either within our ME 199 1-hour and 3-hour curriculum, and eventually, if desired, through senior design and ME 470 as well. So this year we had a few good social events. In the fall we had a bar crawl in addition to tailgates as well as Formula football. One thing we tried to do this year is have team cookouts, so when everyone's at the shop and working, to sort of have some fun as well. In addition, like we do every year, we like to outreach to younger engineers and potential kids who are in STEM. The first of which is the high school tour that we do over Thanksgiving break in some Chicagoland area high schools. Moreover, we also participate in elementary school science nights, local robotics competition, as well as one of the more well-known things is engineering open house at the University of Illinois. where kids from around the area really get to see what we can do even as undergrads in college in terms of hands-on projects. So I'll go over a little bit about this past year's car, who we dearly call Sheila, and its performance in the two competitions. So in Michigan, we were car number 104, and we placed overall 28th out of 120 teams. We had some highlights. We had a second place finish in the presentation event, as well as sixth place in autocross, and we were the fastest only American team, so we were very proud of that. Unfortunately, we were unable to participate in some of the dynamic events, such as acceleration and skid pad, which prevented us from getting the finish that we think we could have gotten. So at Lincoln, we were car number 3, and we ended up placing 21st out of 80. Again, we were able to place 1st in presentation, 3rd in autocross, 10th in acceleration, and 9th or 8th in design. While we finished the endurance event, we were later disqualified due to rules compliance issue in our front wing. So again, not the finish that we had hoped for, but it finished endurance, and it was the 3rd endurance that we'd actually completed, so we were very proud of that. So what were some of the lessons that we learned for this year? First thing is rules compliance. Check early and often to make sure everything passes the rules, because you can finish everything, but if you get disqualified, you lose all the points that we worked so hard to gain. Moreover, we worked hard on getting early component and system design reviews. So in the same vein, we wanted to speed up the process in the beginning of the year to prevent issues that come in later in the year, especially during manufacturing season where the timeline is a little bit more compressed. And of course, as always, we try to pursue a more aggressive manufacturing schedule that allows us a greater testing season, that allows us to break more things early on so that in competition things work. So next I'll hand it over to Tony to talk about our team focus for this year.
How's it going, everybody? So for this year, we had 4 main overarching goals that drove the entire progress of the team. These were weight consciousness, data-driven design and validation, maintain reliability, and an improved student learning experience. So with that, project management this year was very critical to achieve all of those goals. It was centered around an improved gate system, which is our central system for hitting key design and manufacturing deadlines to make sure that we can manufacture the car early and test it as much as possible before competition. This was supplemented by our team wiki or website, which is a central repository for all the design that we do throughout the years and over the years, as well as all testing data that we collect over the years and make sure that we have that so we can iterate on design year after year. In order to pursue more data-driven design and validation, we also increase our efforts to utilize simulation and numerical analysis packages. So we had heavy usage of both FEA or finite element and CFD packages, which we later validated and correlated using physical data during the testing season. On top of that, for competition, since we lost a lot of our fast drivers, which graduated in previous years, we also implemented a new driver training program where new drivers or potential candidates can first prove themselves on a driver in the loop simulator, basically just a computer simulation to kind of get a baseline ranking for everyone, and those drivers were later prioritized for actual seat time to make sure we have the fastest drivers for competition. And finally, since a lot of the season revolved around extensive testing, our aggressive manufacturing deadline helped us achieve that. We got a lot of testing time on the car, make sure that we break all the components early, make sure we can find potential solutions for all of that. And ultimately, all of that was supplemented with extensive data analysis where subsystems would get together after every testing session, look at all the results, find trends, find anything interesting that we're seeing, and further iterate on the design, either implementing changes this year or for years to come. So with that, we complete our team overview, and we'll just get right into subsystem overviews. So I'll hand it over to David Thunga to present for the aerodynamics subsystem.
Hi everyone, my name is David Thunga. I'm the aerodynamics team leader. So on aerodynamics, we design and manufacture the wings and the body of the car. And we set out this year with three main goals. The first one was to improve our simulation model, which we used to design and analyze our aerodynamic package. And we wanted to improve that model to be more accurate with relation to real-life driving. And then also we wanted the simulation model to be a little bit easier for newer members to use so that they can run their own simulations. The second goal was that we wanted to increase overall downforce and reduce the amount of drag that our car sees. And the purpose of that is to improve vehicle handling and just improve drivability for the driver as a whole. And then lastly, we wanted to refine the aerodynamic balance between the front and the rear wings, so try to find a balance between the two to prevent any understeer or oversteer that the driver might see on the track. So I'll go a little bit into the projects that we had. The biggest project was an overhaul of our front wing, as you can see here. And the main design points of that was that we switched from a 4-element main section that you can see on the old car to a 3-element main section that you can see on this front wing. And the main purpose of that was to reduce the amount of overall drag. And then also we had swept wing tips that you can see near the end plates. And the purpose of those is to try to handle the airflow around the tires, again, to try to reduce drag. And then also you can see in the center section of the wing, there's a decambered center section, and that is trying to improve the airflow to the underbody of our car and improve the under tray aerodynamics. And from all these design changes, we saw a 23.3% increase in lift and a 35% decrease in drag, which is very substantial. The next major project was a design overhaul of the under tray, as you can see here. So that goes on the underbody of the car. So in past years, as you can see on this car, we have an under tray that runs the full length of the car. And we decided to step away from that and go towards a half under tray, so it only runs half the length of the car. And the purpose of that is mainly weight reduction, but we also saw through our simulation model that running a half under tray has better, almost the same or better performance as the full under tray, so it was worth a redesign. And then another cool part of this under tray is that you can see at the leading edge, sort of in this picture, there are two little holes. Those are NACA ducts that attempt to draw hot air from the engine bay. So that tries to improve the engine cooling and then also improve performance of the under tray as well. And from these efforts, we saw a 60% increase in lift and a 62% decrease in drag, which is also very substantial. So I just wanted to give a special thanks to all our sponsors this year. We couldn't have done it without you. Any questions? Okay, I'll hand it off to James for Chastity.
Thanks, David, for the excellent introduction there. So my name is James Shackmuth, and I am this year's chassis subsystem lead. So throughout the year, we had a couple goals for the chassis for this year. For one, we had a couple parts that were interfering between subsystems, and that was kind of a huge issue when there are moving parts that are interfering. So as chassis lead, I'm not only responsible for the frame, but the integration of all components. So we wanted to take a look at that and see how we could kind of repackage all of the projects on the car such they wouldn't interfere. Also, as David kind of talked about, and Tony, we looked to really improve our simulation models this year. Not only that, but documentation of them, because we haven't really done a good job of that in the past. So it seems like each year every subsystem lead kind of has to learn how to do it on himself. And then finally, throughout the entire subsystem, we look to reduce weight while still maintaining the reliability we've had in the past few years so that we could finish our endurance races. Okay, so as you can see in the picture, this is kind of the new frame that we've made for this year's car. And some of the huge frame changes that we've made this year, for one, we actually raised the engine height. so that we could both repackage drivetrain, as I was talking about. We were having interference with the differential and a little bit of chain scrape on other parts, as well as accommodating the new under tray section that David was talking about, because on last year's car it was a little bit too low, so we were able to see some performance gains by raising the engine. And to make sure that wouldn't throw off any of our handling, we ran some cornering simulations in software that we have to check how our lap times would compare by raising the center of gravity. And then throughout the entire frame, we were using some new simulation methods. We were able to reduce tube weight while still kind of having the same performance of the frame. Right, so as I talked about, we were looking to do new frame simulations. So in previous years, all of the frame simulation has been done in Creo, but this year we switched to ANSYS because it's a little bit more of a robust package. You could build a model and then run different simulations for the entire car. So some of the stuff that we've done this year is torsional rigidity and cornering scenarios, and we also incorporated modal analysis to determine the resonant frequencies of the frame as well as how it responds during those resonant frequencies. So not only doing this, but like I mentioned before, trying to get new members involved so that they kind of know how to do this, and we can continue to improve our models from year to year rather than starting over. Okay. Also, chassis is responsible not only for the chassis itself, but for fuel systems and paddle shifting as well as steering. So for those who are unfamiliar, last year we actually switched to paddle shifting, which means rather than a manual hand shifter on the side of the car, there's paddles on the steering wheel so that you could either upshift or downshift without having to take your hands off the steering wheel. So what we do, we have ignition cuts on upshifts so that we don't have to engage the clutch, and then we have a cable that mechanically engages the clutch on downshifts. I'd just like to take the time to thank all these sponsors for their help in chassis subsystem. We couldn't really have done what we did this year without them, so thank you. Is there any questions at this time? Okay, now I'm going to hand it off for Ben Williams to go over drivetrain.
Thanks, James. I'm Ben Williams, and I'm the subsystem leader for drivetrain subsystem. So this year for drivetrain, playing into the weight consciousness goal, we look to reduce mass in some of our more overbuilt components in the car, and also identify where perhaps we could improve our reliability for components. Also, we look to improve our simulation practices in order to use both more robust tools as well as also knowing standards across all of our parts. And then we also just tried to improve manufacturing processes. So a lot of our machine components, holding them to a bit higher standards, and also just using different methods to perhaps reduce lead times on them. So we'll start off with the inner drivetrain. So that includes our differential and chain drive. So this year we're continuing use of our wave track limited slip differential. We make our own aluminum housing for it, which we get machined out of house. And then this year, one of our main goals for the car was to actually implement a higher final drive ratio, which basically lets us accelerate at a much faster rate. So on the package, we were able to reduce about a pound, and also playing into the chassis changes, we were able to reduce our half shaft angle by about 3 degrees, which eliminates a lot of losses in the system. So continuing on from that, we've also got our outer drivetrain. This includes our hub assemblies. So this is one of those areas that we're mainly looking to reduce weight on this year. So by implementing some new simulation practices, as well as changing up kind of the style of the hub, we were able to actually reduce weight by about 2.5 pounds. We also switched to a hollow drive pin this year in order to both make them easier to manufacture, as well as a bit stronger in certain scenarios. And then finally, we've also been experimenting with using anodized aluminum inserts to house our tripods, which are how we transmit power through our half shafts. Okay. And then finally, for our brake system, in our brake system, we use a custom machine aluminum pedal, as well as race spec calipers and pads. So this year, in order to basically improve the feel and performance of our system, we increased our pedal ratio, which just gives our driver a lot more mechanical advantage. We also switched to a new master cylinder and bore size. And then also this year we were able to implement a stainless steel primary circuit, which will improve the life of the system as well as its performance. So all this basically gives us a more adjustable and more reliable brake system. So yeah, and then finally for testing, we've also implemented some temperature stickers by Brembo onto our calipers, basically to allow us to see whether or not the thermal assumptions we make on paper really translate to kind of what we're seeing on the track, so that we can make further weight reductions if we see we're overbuilt in those areas. So I'd like to thank our sponsors. We really couldn't have got the subsystem day without you, all the help you give us. Any questions? All right. I'll hand it off next to Andrew Mass, who leads the electronics subsystem.
Hi everyone, I'm Andrew Mass. I'm the electronics subsystem leader for this year. So I'll go over a couple big overall goals for the subsystem for this year. So one of them was to make incremental updates to the entire subsystem as a whole. Last year we made a lot of very large changes to a few of the smaller, less projects. So this year we wanted to make larger changes across the entire subsystem. Another big goal was to make an improved data acquisition system, and along with that, help the team promote a greater use of the data that we collect rather than just collecting it differently. And then also, as another goal that most other subsystems have, is to document the engineering process that we did, so that in the future years we can rebuild the subsystem. So one of our most important projects is the power distribution module. Essentially what this module does is intelligently controls all the electrical devices on the car, whether those are fans or pumps or just electronics boxes. So typically on some other race cars, even in Formula CE or just what you might find in production, this you would see just fuses and relays wired together, but this module replaces those, which allows us to create more intelligent control schemes for them. And there's also many built-in safety features which ensure that the car doesn't burn down a competition or anything like that. So this year we made a couple good changes. So we reduced the volume by about 30%, which helps a lot with not only packaging the module, but also reduces weight, which is a good thing, which ties along with our overall team goals this year. And then we also fixed some of the bugs that we had last year that were just obviously good to fix. So another big project that electronics works on is the steering wheel for the car. This is a picture of last year's steering wheel. So some of the main features of the steering wheel is that we have a color LCD display. You can see it right in the middle of the screen there. And that allows us to display different subsets of data about the car to the driver. Pretty much whatever we want, we can code it up, and then they can see that data while driving or even just while the car's in the pits. There's also lots of different driver inputs. So there's toggle switches, buttons, rotary selection dials, things like that. And those allow the driver to change different parameters of the car while driving the track. So this year there was a few changes. We integrated the shift lights into the steering wheel rather than having a separate enclosure for them this year. We also, some of our taller drivers last year complained that their legs would hit the paddles unintentionally, so we made some smaller paddles for the paddle shifting system, and then just adding more data screens as well. So this is a picture of the paddle shifting assembly. Electronics is responsible for the controls side of the paddle shifting system that James talked about earlier. So there's a couple pictures here. On the left you can see an animation of kind of the whole process of the paddle shifting. So the driver hits the paddle, and then the actuator, it's an electric solenoid actuator, fires, which pulls in the gear lever, and that's what actually causes the engine to shift. And on the right you can see a picture of our custom control strategy that we implemented last year and improved upon this year, which is essentially a big flow diagram of changing how the system reacts based on the state of the car. So the last big project for electronics is the data logger. Essentially the goal of the data logger is to just log all of the data of the car. So that data could be in the form of different messages, sensor values, it could be diagnostics or different events. It really doesn't matter what it is. The data logger doesn't care, it just needs to log it. The other main goal for that module is to provide easy access to the data so that the engineers can get it off the module and actually analyze it. So this year we did a pretty large redesign of the data logging system. So we're now able to access the data via either USB port or wirelessly over radio connection, which is a big improvement over previous years when you'd have to actually pull the SD card out of the board, which was a huge pain. We also implemented some other cool features like a battery backup circuit to allow us to safely close files, and also cellular network telemetry. So you can log onto a website and view the live data from the car wherever it is in the world. I'd just like to thank some of our sponsors. They help us out a lot, allow us to do some of the cool things that we do. So thank you. Anyone have any questions? All right. We'll go over to Jake Sheen about engine subsystem.
Hello everyone, my name is Jake Shindelar and I'm the engine subsystem leader for this year. So a quick overview of the engine subsystem. This is our second year using the current generation Yamaha R6 engine. It's a 600cc class engine. It's the largest engine we can use in our competition. This year, like many of the other subsystems, we had a large focus on weight savings, but also a renewed focus on simulations, as well as continued reliability for the system. For calibrations, we focus on fuel savings and transient tunings, things we have had issues with in the past. For our intake design, we tested and simulated multiple different intake geometry designs. We simulated them in GT Power, which is an engine modeling software, as well as doing actual physical testing in our dyno for validations. For the package that we chose for the car, geometries were kept mostly similar. But all models used were designed parametrically so that in the future they can be easily expanded and revisited for future cars. We also implemented a custom return style fuel system, which isn't native to the engine, but can work more reliably in our car. For the exhaust system, it uses an equal length 4 to 2 to 1 collector for the headers, as well as a custom tertiary and a 14-inch carbon fiber muffler, which we design a custom resonance-based silencer for to help meet our sound restrictions for the competition. For the dry sump lubrication system, this is a system that handles all the oiling for the engine, which is very critical to the engine's reliability. It's designed around a custom dry sump oil pan that's lightened compared to the stock system and lighter even so from last year's system. It uses 2 opposing pickup points in each corner of the engine. This is designed to maximize and keep consistent oil flow to the system. A unique opportunity that we had is we got to work hands-on with one of our machining sponsors, 3 Sigma Manufacturing. We were able to fly out to their facility and work with them hands-on during the machining of this pan, which is, I think, a really unique opportunity. The system also uses a 2-stage daily engineering scavenge pump and a custom-designed Moroso reservoir to complete the system. For cooling, we had a large redesign this year, given the elimination of side pods for the new car. So the system is focused around a dual-pass aluminum radiator that's integrated with the aero package and a custom carbon fiber fan shroud to help maximize airflow through the system, keeping the engine cool. The system also uses, new for this year, professionally sealed BMRS lines and fittings, with the idea behind this of increased reliability and serviceability for a very critical engine component. As for calibrations, it's based around 2 fundamental base maps, one that focuses on maximum power for our dynamic events, and then one focuses on maximum fuel efficiency for our endurance and efficiency events in the competition. These maps are designed around a target lambda or air-fuel ratio table, which is how we characterize the performance of the engine, where we take data for every single operating point that the engine sees in order to find out where our targets are for maximum efficiency and maximum power. We couple this with steady-state dyno calibrations in the engine dyno that we have, as well as on-track transient calibrations, which is everything we can't do in the dyno, so things like rapid changes in throttle position, things that aren't necessarily steady-state. We also implement ECU-based traction control and launch control, which is calibrated for the 2 surfaces that we see in our competition, so one for Lincoln, Nebraska, and one for Michigan International Speedway. And beyond that, we also use a robust version control system for our calibration maps. It's actually stored in the cloud in GitHub and allows us to be able to analyze different performance between the maps and compare and roll back if necessary. So with that, I'd like to take the opportunity to give a thank you to some of our sponsors that make this possible. We really appreciate all the help we can get, and we appreciate the continued support. Does anyone have any questions? Okay. Go ahead and pass it on to Isaac, who can talk about suspension.
Thanks, Jake. My name is Isaac Neal. I'm the suspension team lead for this year. So, quick overview of the suspension. The goal of the suspension is to keep the tires in optimal contact with the road as often as possible. So we're continuing our tried and true design. So we've got dual unequal length A-arms, and we have dampers that are actuated via bell cranks, and we have pull rods at the front and push rods at the rear. We've got a very adjustable system. We can adjust toe, camber, the acronym of the steering system, as well as the ride and roll rates through spring swaps and adjustable motion ratios. Tony talked about our team goals, and so the suspension team really wanted to achieve these team-wide goals. So for the simulation goal, we had a new focus on FEA and vehicle dynamics simulations, which is one of the projects I'll be talking about in a moment. We also wanted to be very conscious of the weight that we're putting on the car. So we looked at downsizing a lot of the links, as well as downsizing the rod ends as well. We also wanted to improve the student learning experience for all the other suspension members. So I made a very big effort to give tech talks at the weekly meetings to ensure that the suspension members are being brought up with all of their theoretical knowledge. So there's a couple new projects that I'd like to go over. So the first is we're using a new lap simulator. We also did a good amount of tire analysis and testing. We also have a new rear anti-roll bar. So first is lap simulation. So right now, this picture might not look very impressive, but actually it models our car's vehicle dynamics on a test track. And that test track is actually Formula SA Michigan's endurance track. So we're simulating our car on the track that we'll actually compete at. So that's a very big advantage for us over other teams who might not be doing these simulations. So this involves creating a model of our car. All of the subsystems have to build this model. And then we, like I said, built the FSE tracks, and then we can quantify different effects of our car. So if we're trying to make an engineering decision on the tires we're using, we can use this software to make an informed decision using actual data and numbers. The next project is tire analysis. So like I mentioned, the suspension is designed to keep the tires in optimal contact with the road, so we have to understand tires. So that's what this project is focused around. So we have raw tire data available to us, and so we look specifically at 3 different tires, Hoosiers and Goodyears, mounted on 10 or 13-inch rims. And then from this we were able to create different tire models and then select a tire based on lateral grip, the amount of feedback it gives the driver, as well as its performance in braking and acceleration, as well as weight. So we've chosen new tires this year, so look for those when the car is unveiled. So that comes out to about 8 pounds of weight saving. So that's rotating, unsprung mass weight saving. So that's pretty huge for us. So last is the rear anti-roll bar. So this is a photo of it here. You can see that at the rear of the car. So the purpose of the anti-roll bar is to increase the roll rate of the rear suspension. We also wanted to design it to be adjustable. So this little animation you're looking at here shows how we can swap the bar in. So you have different tube thicknesses, so that changes your roll rate. And then you can also adjust the length of that lever arm there. So the purpose here is that we'll have faster transient response to cornering, so when the driver gives a steering input, the car will react faster. We also want to make sure that we're reducing the weight of this component as much as possible. We want to be very conscious of the weight we're putting on the car. So this was designed for a total mass of under 1 pound, so we're pretty proud of how that worked. So before I open the floor for questions, I'd just like to give a special thanks to all of our sponsors. Without their help, the suspension team would not be what it is today. So thank you. If there's no questions, then I'll welcome up Tony to talk about composites.
How's it going, everyone? again. Not only do I lead the team as team captain, I also lead the composite subsystem, so I'll talk a bit about that. So the big overview for this year was to just reduce a lot of weight over the entire car. We were actually able to reduce the entire weight by 14 pounds across various subsystems through the implementation of various carbon fiber components, which was huge for us this year. In addition to that, we also increased the number of composite components throughout the car, so pretty much every subsystem now features some sort of carbon fiber part. And then we made a big push to streamline the manufacturing process so that we can increase the part volume. So for manufacturing, we really enhanced our CAM and CNC practices. We're using more industry-style practices to make sure that all of our tools and molds come out properly, as well as pursuing parallel manufacturing. So rather than making a single part at any one time, we use our team wiki or team website to track the status of every single part in the entire manufacturing process and create multiple parts at the same time. And in addition to that, we follow the team-wide aggressive manufacturing schedule so we can have the parts on early on during the testing season. In addition to that, we also moved towards exclusively pre-preg or pre-impregnated carbon fiber design and manufacturing, so that drastically reduced the weight of all the parts across the car, as well as helped us to really ease the manufacturing process. In addition to that, we also improved the cure cycles to get better quality parts, which aided in both surface finish, which helps out the aerodynamic subsystem, as well as reducing the weight of the parts. In addition to manufacturing, one of the big projects that Composites had this year was to develop a set of carbon fiber suspension parts. So primarily the steering and toe links, as well as other ones that will be implemented in the future. These helped out by just reducing weight overall in the car, and since they're on the suspension side, they really help the vehicle dynamics characteristics of the car, as well as reducing the suspension compliance, which is critical to making sure that the suspension behaves the way that we model it, and also gave us increased research into industry bonding practices to make sure that these parts actually hold up throughout the entire competition. As with all the subsystems, I'd really like to thank the sponsors that help us out with. Composites are really difficult to pursue, especially in university. So with the help of them, we're able to do a lot of these cool things on the team. Any questions? Cool. So with that, I'll lead into our unveiling video.
We'd like to thank you again for coming out today and invite you guys all up for pictures and questions. Thank you.
Maybe we can play this. first curl.
Should we get a picture of that?
So we're working with last year. And what,
Stop this.
and how many plates did you get?
My computer's like screwing up. Oh, no, it's still.
And what's the